Oh, why it's training for so long. And I need to reduce the batch size to begin with. Yeah, but it starts being jumpy like that. It's probably not a good sign. Then it doesn't really converge. Also not a good sign. It is converging. Slowly but surely. Yeah, the loss function got to a pretty low number. Doesn't look like it did very well at the end there. Can try a different activation function, maybe restart. Yeah, you can on the fly while training, you can change parameters and hit the train neural net button again. See what difference it makes, if any. Yeah, we're really after the edge cases. So for example, you can add more noise. Where's noise level? 2 is maximum. Let's bring it back to tan H. I don't know how to pronounce it. Yes, we get now more noise in the signal, and we expect the neural net to struggle more. And yes, the loss function only gets to 0.4. You can see the conversion is not great. But this is deployed. This is in production. You have this description that you can read.
This application is a web-based neural network training interface that allows users to train a neural network on the fly within their browser using TensorFlow.js. It's particularly useful for educational purposes, to visualize how different parameters affect the learning process, and for rapid prototyping of simple neural network models. Here's a breakdown of the different controls and how they can be used. Training set size. This slider adjusts the number of data points used to train the neural network. A larger dataset can potentially improve the model's accuracy but may take longer to train. Hidden layer size. These sliders control the number of neurons in the first and second hidden layers of the neural network. More neurons can capture more complex relationships in the data, but also increase the risk of overfitting and require more computational resources. Noise level. This slider adds a certain level of randomness to the training data, simulating real-world data imperfections. It helps to test the robustness of the neural network against noisy data. Learning rate. This is a critical hyperparameter that affects how quickly the model learns. Too high a learning rate can cause the model to converge too quickly to a suboptimal solution, while too low a rate can slow down the training process significantly. Epochs. This slider sets the number of times the learning algorithm will work through the entire training data. More epochs can lead to a more trained network, but also increase the risk of overfitting if too many are used. Batch size. This determines the number of samples that will be propagated through the network before updating the model parameters. Smaller batch sizes generally require less memory and can update the model more frequently. Activation function. This dropdown lets the user choose the activation function for the hidden layer. Options like ReLU, sigmoid, and THAN dictate how the neurons in the network will transform the input signal into an output signal. Optimizer. This dropdown allows the selection of the optimization algorithm that will minimize the loss function. Choices like ADAM, SGD, and ADAGRAD offer different approaches to the learning process. Loss function. Through this dropdown, the user can choose the loss function the model will use to compute the quantity that a model should seek to minimize during training. Options include mean squared error, mean absolute error, and mean squared logarithmic error. Train NN button. When clicked, this button starts the training process with the selected parameters. It's the action trigger for the model to start learning from the two charts display in real time the performance of the neural network. Prediction chart shows the actual data points versus the predictions made by the neural network. Training loss chart illustrates the model's loss over each epoch, providing insight into how well the training process is going. Overall, the application can serve as a didactic tool for understanding neural networks and a practical instrument for researchers and hobbyists interested in experimenting with machine learning without needing to set up a full-fledged environment. Understanding fluctuations in neural network loss during training. If you're observing fluctuations or jumps in the loss, especially if the loss increases sharply at certain points, this could be due to several factors. Learning rate. If the learning rate is too high, the model may overshoot the minimum of the loss function. The learning rate of 0.04 could be too high, causing instability in the training process. Batch size. A batch size that's not appropriate for the dataset might cause erratic updates to the weights, leading to fluctuations in the loss. Optimizer. Although ADAM is robust, it might still require tuning of its parameters, like learning rate schedules or beta values, to stabilize the loss. Data quality. Make sure the data is clean and pre-processed correctly. Anomalies or outliers can cause sudden changes in loss. Model complexity. Ensure that the model is appropriate for the task. Both underfitting and overfitting can cause erratic loss patterns during randomness. Stochastic processes in training can cause variability. This includes the random initialization of weights, random shuffling of the dataset, and randomness in dropout layers. If loss calculation, ensure the loss is averaged correctly over batches and epochs. Summing losses without averaging can cause misleading spikes. To reduce the fluctuation, try a smaller learning rate or use learning rate schedules to decrease it over time. Consider tuning the batch size, starting with smaller batches and increasing if needed. Introduce techniques like gradient clipping to limit the effect of very large gradients. Implement early stopping to hold training when the validation loss starts to rise, which can prevent overfitting and reduce the likelihood of these spikes. Use a more complex model evaluation approach. Instead of just looking at loss, also look at validation metrics. Loss might not tell the full story, especially if the distribution of errors is. Remember that manually fine-tuning hyperparameters can be quite tedious. You might want to implement a more systematic approach, like a grid search, random search, or even more advanced methods like Bayesian optimization, to find the optimal set of hyperparameters. When training neural networks, especially when using stochastic algorithms like SGD, stochastic gradient descent, or its variants, like ADAM, is expected to get different results across runs even with the same initial parameter. This is due to the inherent randomness in the training process, including but not limited to random initialization. Neural networks typically start with randomly initialized weights. Even slight differences in these starting values can lead to different training paths and results. Data shuffling. If the training data is shuffled before each epoch, which is common practice, the order of data seen by the network changes, which can affect the updates to the model. Stochastic gradient descent. The optimizer itself is stochastic. ADAM, for instance, calculates adaptive learning rates for different parameters from estimates of first and second moments of the gradients. The stochasticity in the gradients will lead to different updates. Hardware. The computation may involve floating point arithmetic, where operations can be non-associative due to rounding errors, leading to small variances. Parallelism and concurrency. The way computations are parallelized on the CPU, GPU can also introduce non-determinism. Improving neural network performance for sinusoidal function prediction. For a neural network model tasked with learning a sinusoidal function without noise, achieving a near-perfect prediction is feasible, especially if the network architecture, learning rate, and other hyperparameters are suitably chosen. Here are some suggestions to fine-tune your existing setup to improve model performance. Simplify the model. Since the task is to predict a sinusoid, a simple model should suffice. You might not need 2 hidden layers. Try with 1 hidden layer first, and only add a second one if necessary. Hidden layer neurons. You may not need as many neurons. Try starting with a smaller number and increase only if the model performance is not satisfactory. Learning rate. The learning rate may be too high, leading to overshooting the minimum loss. You should consider lowering it or using a learning rate schedule to decrease it as training progresses. Activation function. The choice of ReLU, rectified linear unit, is fine for hidden layers in many cases, but since the sinusoidal function involves both positive and negative values, ~than might be a more suitable choice as it outputs values in the range -1, 1. Loss function, mean squared error, MSE, is appropriate for regression problems, and since you're predicting a continuous value, it's a suitable choice. Epochs and batch size. Your choice of 200 epochs and a batch size of 10 seems reasonable, but these may need to be adjusted based on the model's learning curve. Optimizer. ADAM is generally a good optimizer, but if you find the loss fluctuating too much, you might want to try SGD with momentum or experiment with different hyperparameters for ADAM. Randomness. TensorFlow.js, like many deep learning libraries, includes randomness in weight initialization and data shuffling. While you can't set a global seed, try to ensure consistency in other ways such as data preprocessing and model initialization. Regularization. If you have a larger model or add noise later, you may need regularization techniques like dropout or L1 per liter 2 regularization to prevent over. Data normalization. Make sure the input data is normalized or standardized if you start working with more complex or varied datasets. Evaluate on unseen data. Ensure that you're evaluating model performance on a separate test set that the model hasn't seen during training to get a true measure of its predictive power. Experiment systematically. Change one hyperparameter at a time to see its effect on the model's performance. This can help you understand which parameters are most sensitive and need careful tuning. Based on these suggestions, you can adjust your training script to conduct more systematic experiments and converge on an optimal set of parameters that yields the best performance for your sinusoidal prediction task.
Yeah, obviously this is a much simpler model. Doesn't require that much detail. So these parameters that are set by default seem to work okay-ish. Okay, to 0.12. If we reduce noise, should in theory go lower. Yeah, when it's jumpy like that, it's not a good sign, but might still converge. Still 0.14 or so. It's gonna go any lower? Yeah, probably not. Adding more data points. Seeing at 0.1 something at the moment. It can get all the way down to 0.01. Yes, now it's 0.06. So I have the training set size is 100, doesn't make much difference. Number of hidden layers 5. A second hidden layer size is 3. Noise level 0. Now learning rate. Just try edge cases. That's obviously too small. Still manages to converge 0.05. Yeah, I'm not sure how learning rate affects the result. Doesn't seem to make much difference in this case. We do need some nice thumbnails for we'll do those, and so we can post the results. It would be good to have example images there as well, potentially. That would be more useful while we edit. Some sort of like comparison of two. Actually pop it into, so yeah, the aspect ratio of it might be not great. To default values as well. This one has some noise in it. Could be nice to have the final result. Yeah, if we're sending data to the server, because currently the Flask application doesn't have a backend. Well, it does have a backend, but it doesn't do anything. We could use the backend to send to store results. That might be too complicated, maybe. Yeah, we like different examples. Let's pop the noise level all the way to 2. See what happens. We expect the loss function to be much higher and not much convergence happening. That's right. Let's do an example like that. So this one converged, the first one converged much quicker. This one has a lot of noise in it. We already had the default value, didn't we? This one for some reason is different. Yeah, there's that non-deterministic aspect of it. Even between runs with the same settings, you get different results. But get different results. So we already have something similar to a learning rate of 0. A bunch of examples there. Yeah, Adam doesn't do well. No, it does. It takes longer. It might be enough. The rest you can try the tool yourself. I don't want to give you all the results, do I? Go check out BioniChaos.com and don't forget to provide your feedback. See you next time. Bye. Can do some music at the end if it works. Might be loud. Beware.